mini course is considered for master and PhD student, and also some enthusiastic mathematician like now about this subject. First of all, we consider and fix some notations which need in the continuing of these lectures. Let throw out this lecture. We assume that are a polynomial rings, which K is a field, and R is a polynomial rings. And xn and x1 and xn is a variables. So
just a question.
Yes.
Is there any restriction on the base field, on the characteristic of the base field, or not? A priori, no restriction on characteristic on the field, right?
Yeah. No, the K is any field.
Any field. Okay.
Yeah, any field. And in zero is the set of non-zero integer. Non-zero integer. We start with some basic and elementary definition of polymatroid ideals, because this is the course is for master. We need some background for the continuing about this subject. Definition: U x a1 xn an. This is the monomials. Monomial element. This is the product of the variables. So with a is n0 is called a monomial element. Monomial element. And we write for the simplicity, we write U is equal to XA, which A is A1, a vectors. Is a vectors. So, and we have XA, x power A, multiple x power B is equal to XA plus B for all, and B is non-zero integers. And also degree of XA is equal to these numbers. Is equal to this. So suppose the mono R is a set of monomial ideal. Is a set of monomial ideals. Monomials of R. All of monomial collecting in the set of mono R. which is this monomials is a K basis, which a K basis is a vector space, K basis of R. And also for every and also for every F in R, we can write sigma A U X U U U is a monomial. For every F in R, R is a polynomial, these polynomials, as you see here. So if we can write F is a polynomial, and so we can write F as this direct sum, this summation. Also, this A is element of K. Also, support of F is equal to these numbers, these the monomials, such that AU is non-zero. Is the support of F. Oh, F. And by this definition, and when we look the mono R, we have this equality. Mono R, we can write this one is union of support F. F is in R. We can write this equation. And also a monomial ideal. What is the name of monomial ideal? What is this? What is what is the mean of monomials? Monomial ideals. An ideal I of R is called a monomial when I generated by monomial element. By monomial element. So monomial element, if you look to this one, this is a monomial element. I is generated by these monomials. So as you know, the polynomial ring is a Noetherian. So every monomial ideal finitely generated. And also when we have I is a monomial generated by monomials, by Dickson theorem, Dickson lemma, we can find a finite number of monomials such that generated I. This is the known. This is the easy lemma. So also we have some facts that I be an ideal of R then I is a monomial ideal, is a monomial ideal if and only if this is the definition and this is the equivalent. I is let I be a monomial ideal if and only if for all f in R f belong to I if and only if support of f contained in I. This is the definition of the support. For the proving the I is a monomial, it is enough to prove this equivalent. So let I be a monomial ideal. Let I be a monomial ideal of R. Then the set I U plus I such that U in mon R minus I, this set belong to mon R minus I is a k-basis of the residue field. The residue clusterings plus ring R mod I. This is the vector space. The basis of this vector space over K is we consider as this set. So in fact 3 we have let I is equal to U1 and UM be a monomial system of generated. System of generated of I, then V is a monomial belong to I if and only if I is generated by these systems. This is a system of monomial generated I. V belong to I if and only if Vi divide V which I there exists between 1 and M. So what is mean Vi divide V means that V belong to the principal ideals. I between M and 1. So when we belong to I, if and only if we have these conditions. So this is the fact, but also this is the very mini theorem. The proof of this theorem is very easy, and because I want to reach to some goal I consider, maybe I escape from some theorem. And definitions. definitions. We come back to this one. So suppose U is equal x a1, xn an, and v is equal to b1 and xn bn is the monomial elements. Two monomial element of element of R. So we say that U divide V is definition. When we have AA less than and equal to BA for all A. In this case, we write U divide V. Since R is a UFD factorial domain. R is a factorial domain. Factorial domain for all F and G belong to R. There exists the greatest common divisor. And we write GCD. This element exists because this is the factorial domain. And the lattice and the list. And the least common multiple. So this one is the LCM. These two elements, they exist because R is a factorial domain. So we have GCD for these two elements, U and V, is equal to X1 min A1 and B1, X2 min A2 B2. So Xn power min An Bn. This is the GCD. GCD is equal to these numbers. So LCM, U and V is equal to X. This is the maximum. A1, B1, X1. X2 is equal to maximum A2, B2. And so on. Xn is equal to maximum An, Bn. This is the LCM. For examples, let's see an easy examples. Let U is equal to X1, 3, X2, 4, and X3, 1. And V is equal to x1, 2, x2, 5, x3, 7, for example. And GCD, then GCD, U and V, minimum between 2 and 3, x2, minimum 5 and 4, x4, minimum 7 and 1 is the power of x3 is 1, is 1. And LCM, U and V is equal to the maximum 2 and 3, 3. And the maximum of 5 and 4, 5. And the maximum of 7 and 1, 7. This is the LCM. So we have the following lemma. If you have any questions, we could ask the questions. Let I and G be monomial ideals. Be monomial ideals, then I is the basic theorem for constructing of the monomial ideal. For example, I and G be a monomial ideals, then I plus G and I multiple G, and also intersection I intersection G are monomial ideals. Monomial ideal, in particular, I intersection G is equal to generated by this set LCM U and V such that U belong to the generated of the minimal generated of A. We write I and V, the minimal generated of J. Here, Ji is a minimal generated of minimal generated element of I, and note that as I said, the minimal generated of a monomial ideal with respect to divisibility is a unique U. So GI is the unique U minimal generated element of A. And I know that every minimal generated of a monomial ideal is finitely generated. And so the computation of LCM is not very hard. So for the proof of the if I and J is a monomial ideal, this is an easy because we use you use the fact the A with the fact I, very easy. F in here, so F writing writing sum of J1 and J2, and so the support of J1 contain in A and support of JD contain and G, and the union of this support contain and the union of to this. And so for this one, the same. And so we want, this is easy, but we want, this is important. We prove this and in this case. So proof it is clear A plus G and A multiple G is monomial ideals, are monomial ideals. So for the intersection, let F in intersection, then we have F in I and F in J. And so F is a monomial, so we have the support of F contain I and support of J, support of F contain J. This one. Then support of F contain a intersection J. So F is said that A intersection J is monomial ideal. So we want to prove this set. These two sets is equal. So let suppose W in the support of F. We consider one arbitrary element of the support of F. F is a arbitrary element. So then support of here writing here, since support of F contain I and J, there exists and the W in here, so W in here, and so by by the tree in the fact tree we have W there exists. There exists there exists U in JA and the V in JG such that because W in intersection by the fact 2 we have V U divide W and B divide W, and so LCM U and V divide W. So thus the A intersection G is contained in this ideals LCM U and V such that U in JA and B in JG, because one element can consider in here, and so through that element in here, because this is the this set that U in here in this, so we have intersection contained in the this set. And come back to So we want to the conversely of this. On the other hand, since LCM U and V belong to A intersection G for all U in GA and V in GG. So we, on the other hand, since LCM in this intersection, we conclude that because why this is here, because every element of I is divided this, and every element of divided this, and so this is here, and so this is clear. We conclude that this ideal LCM U and B U in GA and V GAG, this ideal contained in A intersections, and so we have the equality, and so we have the results. Examples: let A is equal to x3, xy, and y4 power 4, and J is equal to x2 and xy2. Be two monomial ideas. The two monomial ideals of these things. Yes. So then A plus G is easy, is equal to x3, xy, and y4, y power 4. This means our y power 4, for simplicity, we say that y is 4. And J is this one, x2, xy2. This is equal to x3, xy, and y4. And so x2 and y2. So this one is bigger than cancelled. So this one cancelled, and so we have x2, xy, and y4. This is the sum of I and j, and so the multiple of j is equal to multiple of these elements, and x4 multiple of the component of x3 multiple x2 and x3 multiple this one. So we have, and also this one multiple x2, this one multiple of y4 2, and so y4 multiple this one, and y4 multiple this one, and this ideal equal to, for example, x5 x4 y2 and x3 y and x 2 y3 and x2 y4 and x y6. This is equal to some of element cancelled. For example, this one cancelled because this is this contained in this ideal. This element belong to this ideal, and so x y5 5 6 contain no, and x2 y3 and x3. We have this one x5 x5 x3 y, this one, and this one contain here cancelled, and x2 y3 and x y6. This is the multiple. And also intersection. By intersection, we use this and using this for intersection of J is equal to LCM. This we have two elements, x3 and x2, and LCM x3 and xy2, and LCM xy and x2, and LCM xy and xy2, and LCM y4 x2, and LCM y4 xy2. This is equal to I intersection J is equal to this set. This is the x3, this one x3 y2, this one LCM is x2 y, this one x y2, this one x2 y4, and in end x y4. So the ideal generated by x3, this one can belong to this one, is cancelled. This is the x2 y and x y2. Also, this one belong to this is cancelled, and also we have x y4. This is the intersection. The intersection of I and J is equal to this. These are generated x3, x2y, and this is the belong to here, and so we cancel. So and we can remark if I is equal to U1 and U T and J is equal to V1 Bs generated by this monomial are monomial of R are monomial ideals. Ideals of R. Then we write for simplicity, I plus G is equal to Y1, YT, and the V1, Vs. This is the, and also I, G is equal to Y, U1, V1, U1, V2, and U1, Vs, and continue. And also U, U, T, V1, and UT, Vs. This idea. And also we have for the intersection, we have the same of this. We want to, okay. And definition, we want to define the colon ideal of monomials. Let I and J be two ideals of R. The city, then the city I, J is the colon of I with respect to G is equal to all F in R such that F G belong to I for all F G in GHG. This is the ideal generated by this. This is equal to this sets. So, and this is an ideal, of R, and is called colon ideal. And colon ideal of A with respect to G. And note that the sum of two monomial ideal is monomial. The product monomial ideal, two monomial ideal monomials, and intersection of two monomial ideal is monomial ideal, and also the colon ideal of two ideals, two monomial ideal also is monomials. And we prove this lemma. Let I and J be two monomial ideals. ideals, then I J colon of A respect to G is a monomial ideal. Is a monomial ideal, and I J this colon ideal is equal to intersection of A V V in J J is equal to this one. And furthermore, I V this colon is equal to this set U GCD U V plus that U in GA. This colon ideal is equal to this one. So we want to prove this is the monomial ideals. We consider one element in here and prove that the support of this element contained in these ideals. Okay. Proof. Let F this colon ideal here, and so as a definition, F V contain is A for all V in G. Yeah. So since support of F V, this is equal to V is a monomial element. Support of F V is equal to support of F V. This is contained in A because the F because F V in here I is a monomial ideal, and so support of FV contained in I. Then and from here we have support of F contained in a V in this one for all V. This is for all V. V in GA. GAG. So for all V in here, so support of F V in here for all V. So we have support of F contained in this one. And this said that I in J is monomial ideal. Monomial ideal. Also, it is clear because the J is generated by finitely generated. So this is very clear. We have very easy because every element in here we concluded in this element in the right hand, and so this equality, and it's clear I J is equal to intersection of A V V in JG by the consider element in the left hand, we conclude that this element in the right hand, and so conversely. So we want to suppose we want to prove the end of theorem, this one. Suppose W is equal to V divided GCD of U and V. We consider element in here. We conclude that this element in the left hand. Suppose W is equal to this, then W multiple GCD U and V is equal to U, and let GCD of U and V is equal to V multiple alpha. This alpha exists because GCD divided the V, and so there exists alpha in mono. So then omega and this considered as this one omega GCD omega GCD. This is omega GCD U and V. This is equal to U, and this equality multiple in alpha. So this is equal to W and V. This conclude that this is the W and alpha, this one contain in V the element of I. This contain in I. So you alpha in here, and so this one W contain in a V, contain in here, and so this set contain in these ideals. So this set, this ideal U GCD U V U in GA, this one contain in a V, this ideal. And for the conversely, we have this one. Conversely, let omega in A V, then then U omega V divide I. And so I is a monomial ideal. Then there exists U in G A such that U divide omega V by the fact 1. So this said that U GCD U V, this is divide the V GCD U V omega. But this element and this element is a coprime. We have this element divided this one. And so U GCD UV divide omega. It said that omega in this set. U in G. And this is element in omega in here. So we have A, B, and cedar and this set. We have to, and so the result true. The result is proved. The proof is complete. So examples. Let's see one examples. Examples. Let A is equal to x3, xy, and y4. The previous example. And J is equal to x2 and xy2. Then I colon I j colon I with respect to j is equal to by this one. By this one, we have this intersection for our element. Element of j is 2, and so a x2 intersection a xy2. And the colon ideal equal to this one by this lemma, this one. This one for the finding the element of this one is looked to the end of the lemma. This is equal to the element of E, x2, x3, this one, GCD, x3, and this element, and x, y, GCD, x, y, and x2, and y4, GCD, y4, and x2. Intersection, this one. X3, GCD, x3, and xy2. And xy, GCD, xy, and xy2. And y4, GCD, xy, and y4, and xy2. And so we have this ideal, GCD of this ideal. This one, GCD is x2. So this one, GCD is x. And this one, GCD is 1. So this one, x, this one, y, and this one, y4. Intersection, this one, x3, the GCD of this ideal is x, GCD of this ideal, xy, GCD of this ideal is y2. So this one is x2, and this one, 1, and this one is y2. So this is the whole ideal R. And so we have, and this one contain the ideal is y, and so is equal to xy. This is cancelled because y4 belong to ideal generated by y is equal to this one. So this is equal to this. So examples. Let I, J, and L be monomial ideals. Be monomial ideals. Then A, I intersection J plus L is equal to A intersection J plus A intersection L. This is in general is not true. I know that in general we consider A contain G, but for monomial ideal, this in general is true for monomial ideal. But if you consider if the ideal is not the monomial, we don't have this equality. We have one this direction. And this is also true for our idea for all ideals. But for monomial ideas, the equality true. So for the proof, it is clear the the right hand I intersection J contain in this one because J plus L, because J plus L bigger than J, and so the intersection in the right hand bigger than the intersection of the left hand. And also for this one, I intersection L. This is contained in here. And so the sum contained in the right hand. So A, this is clear because this contain here and this one contain in here, and so the sum of two ideal is contained in this here. For the conversely, suppose f in here J plus L. Suppose if in here, then support of F contained in I, because I is a monomial ideal. And also support of F contained in here because J and L is monomial ideal. And so the summand of J and L is monomial. And so the support is contained this ideal. The support is contained because I is a monomial ideal, is monomial, intersection is monomial, so the support of this is here. So let omega belong to support on. Support is the set. Omega in here, and so omega in here, so omega in belong to I, and so omega belong to I. We have U belong to I, there exists U belong to I such that U divide omega, because I is generated by monomial ideals. And also omega in this summand, omega in here. So there exists V1 in J, or V2 in L. This is the monomials here. GA, this is JG, this is JL. There exists such that V1 divide omega, or V2 divide omega. So we have this one. Therefore, V divide omega and or V1 divide omega, or U divide omega and V2 omega. This one said that LCM U V1 divide omega, or LCM U Y2 divide omega. And so we have LCM U Y is UY. Okay, we said that omega is this one, L I intersection J, and this set I intersection L. And so for all omega in support, we have this one. So the support, all element of support belong to this one, and so we have the equality. And so is A intersection J plus L is contain A intersection J plus A intersection L is set, and this complete the proof. Completes the proof. So we have this equality for two ideas. We can generalize or extend. For example, as the corollary or remark or corollary. Let I and J1, Jn be the monomial ideals, ideal of R. Then this is the a key lemma, a key example. Very in the continuing, we very using in these equations. Monomial ideals, then I intersection sigma Ji I 1 to M is equal to the intersection I 1m I plus ji. Easily from by induction, we prove that this one is easy because this is true, and so by induction, we have this. This is the excuse me, this is the intersection. And so this is a sum. 1, 2, m. Intersection I intersection j I. This is sum. This is by induction. We have these equations, and so the another corollary. If I, j, and L are monomials, ideal, then I plus j I plus g intersection I plus L is equal to I plus j intersection L. This to it here. This is easily since that we have this because by using this exercise, we want to prove this one. So for this one, this corollary, A plus G intersection A plus L is equal to A plus G by the exercise. This is the new ideal, for example, A1. A1 intersection by this one and A1 intersection by L. And A J intersection L. So this one A plus G bigger than A. So the intersection A. And here again by exercise examples is equal to A intersection L plus A J intersection L. This one containing here I bigger than the I intersection L. So this is equal to A plus J intersection L. So we have this one. A plus J intersection L. This is very easy, but very practical. This one, very practical in monomial ideas. So we can generalize this corollary. Let A and J1 and Jm be a monomial ideas. Then A plus G1 intersection A right here this intersection A1 to M, I, this is equal to I plus intersection GI. This intersection is equal to right hand and the left hand. This is nice. And also, and another examples. Let I is equal to U1 and U R be a monomial ideal. Monomial ideal, and V is a monomial element. Monomial elements. Then A I colon V is ideal is equal to this direction. A1, 2. This is nice. This column. This column ideal equal to this solid. And conversely, for the proof of this one, we use the by choosing the element from the left hand and prove that this element in here, and conversely another element in here, we prove that the element in the left hand. So it's clear. Here, this one contain in A, B, because A bigger than this one. Every element in here, in the left hand, we have this element in the right hand. So this in here, and so we have sums contained in here. So for conversely, suppose alpha in A V, alpha in A colon V, such that alpha is a monomial element. Monomial element. Then alpha V by definition in A. We have this one. And so again, by definition, UI is element of the I in this the monomial. Divide this one. In this one exists. So this implies that alpha V in here, and so So we have alpha in Vi colon V. So alpha in here and alpha in the direct the summand. So consider alpha in here. Prove that alpha in the this. Then so this is equal. And this complete the proof. And so this is true. And so this complete this proof. But if you replace instead of V ideals, monomial ideals, this is not true. Note that in the for the this is very important. V is a monomial element. If you consider instead of V ideals, colon I with respect to J is not to direct sum of the this one. So note that for this is very uh, uh, yes. Let me write an example. In here, note that if consider uh, consider monomial ideal G instead of monomial elements V, then then let me write in alt a star, then a star the equality of a star in general is not true. So for example, let I is equal x to y and x and z and j is ideal x and z. So this ideal this column ideal j z x z this is equal to xy and z, but a x to y and z x plus x to y z z equal to this ideal is xy and z, and this one this is r. because 1 in here. So is equal R. And this, we don't have it equality. Is ideal equal to this one, but the direct sum, the summand, this summand is not equal to the colon ideal. So this is true only for monomial ideals, only for monomial ideals. So, but in general, we write this one. A, write as a fact, fact, let I and J1 and JR be a monomial ideal. Be monomial ideals in R, then in general, for R ideal, we have these facts. I sigma J, this colon ideal, and R is equal to intersection A J A is equal to this. And so we want to define the radical ideal. Radical ideal of monomial ideals. Mission get I be an ideal of R, then the ideale radical A is the set of F in R such that F power K in I is K in N. Radical ideal defined by this set, and radical ideal is ideals. It's called the radical of I. And it's clear every element of I in the radical, and so I is contained radical. It's clear I contain in radical ideal. And if in the continuing, we prove that the radical ideal of monomial ideal is monomials. And if I is equal to radical I, we said that I is a radical ideals. Then we say that I is a radical ideal. For example, every prime ideal, is radical ideal. So we familiar with one radical ideal. The prime ideal is radical ideal, and in the continuing we see some another radical ideal, which is not the prime ideal. Is the radical ideal, but the radical ideal is not necessary. Every radical ideal is primary. It's a prime ideal. So let me define the square free monomial ideals. A monomial element element x power a is called square free if all component of a are a is a vector space. Is a vector of is the element of a power n is a 0 I are component of I are 0 or 1 0 because a uh, is equal to a1 and an belong to n 0. In the previous defined this vector elements. A monomial ideal I is called a square free. It's called a square free monomial ideal is called a square free monomial ideal if I generated by a square free monomials. Square free monomials. For example, I generated by xy, xz, zu. This is the square free monomial ideals. This is square free. Square free monomial ideal. But this one is not square free. Because the power of x is 2. All power 0 and are 0 or 1. 0 or 1. This is not square free. And we want to remark and to say this remark because I want to find the prime ideal. The prime ideals, every monomial prime ideals is a square-free monomial ideals. If some generator of some minimal generated generator U of a monomial ideal I is of degree U bigger than 1, then I, if some minimal generated U of a monomial ideal I is of degree U bigger than 1, then I is not prime ideals. Because since if U is equal xi v, and then U is a one of the element minimal generated of one of the element of minimal generated of A. So we can write U is equal to x1. This exists and V exists. V minimal and this minimal, and then U is a monomial element of the generated of J. Then x1 is not in A. Also V is not A, because this is the element of monomial generated, and so but xiv in I. So this said that I is not prime. Then I is not prime. If so, this tell us every monomial ideal of R generated by the element of degree of 1. So if all elements, all elements, all generators all generators generators all generators are of degree 1. Degree 1, so that I is generated by a set of variables. A set of variables, then I is a prime. Prime is a prime ideal since we have this isomorphism. I and this is the domain, and so this is the prime. So it is a domain and integral domain. So so x1 and xr is prime ideal, and note that every prime ideal generated by the computation of the variables. Every monomial prime ideal generated by computation of the variables. Also, the only maximal ideals, the only maximal monomial ideals, ideal of R is this one. So so the polynomial, this polynomial ring has only maximal monomial ideal, has only one maximal polynomial. This is the only maximal has many maximal ideal, these rings, but the maximal monomial ideal is the one, but maximal monomial ideals. So lemma a, a monomial, a square free, monomial ideal is radical ideal. In previous, I said that every prime ideal is a radical ideal, but every radical ideal is not a prime. So, for example, a square free monomial ideal is a radical ideal. Proof. Let I generated by V1 and VR is the square free. Every generated is a square free, and so with V I is equal to VI1 XI1 XI1, and let me write here U1 is equal to XI X1 is 1 and X1K here. Then I is equal, using we want to use Monaf theorem, U1 is ideal. Let me write for the simplicity. Plus Y2 and YR. We can write I as this summand. And so this one, X1, 1, because the power, the product is equal to intersection, because GCD is GCD is this one is 1. So X1 2 X1 K plus U2 and U R. As the exercise proved in the previous, we have this one X1 here, X1 1 U2 UR intersection X1 2 U2 UR intersection X1 K and U2 and UR. And so if consider U2 is equal to X21, X2, for example, L. Then again, the equality of this again here, and so we have A, this one, X 1J and U2, U3, and UR. This is equal to the same of this one, M1 to L, X1J and XU, U in here, U X2M and U3 UR. And continuing this argument, we have we see that I is intersection of ideals of if PM is equal to XM1 and XMS ideal generated by variables. This ideal is a prime, as previous in here I said that this is a prime ideals. These ideals are prime. And so radical I is equal to, for example, P1 and P. P is exist. So this one is equal to P1 intersection PT. Is a this ideal is a radical ideal P1 and PT, and this is the I. So the radical ideal is equal to I. So I is a radical ideal. So I is the radical ideal. This is very nice. Every square-free monomial ideal is a radical ideal. Every square-free monomial ideal is a radical ideals. And the converse of this one is true. Every in the tomorrow I prove that the radical ideal only the only monomial radical ideal is square free monomial ideals. And we have the equivalent a square free monomial ideal is radical ideal. If the ideal is a monomial, the radical ideal is a square free. This is true for all square free. We have this one. For example, let me write in here, calculate the radical ideal of this one. In the start of the my presentation, the voice is the voice is closed, and so you don't hear my voice. And I introduce myself in the first. My name is Amir Mafi from the University of Kurdistan, Iran, and this course is about the topic of monomial and polymatroid ideals. We introduce the monomial ideals very elementary, and so in the next session we have some new results about the polymatroid ideals. For example, let I is equal to x2, y, x, z2, and y2, z. And so then the radical ideal is equal to radical ideal, this ideal as a definitions. It is equal to xy, xz, and yz. And this is a square free. Xy, xz, and yz. So the radical of ideal is equal to this one. This is the radical ideal is a very great definition, very good definition, because by this definition, minimal prime ideal of a I is very easy find. So and so the time is finished. That's all for today. Tomorrow we continue the presentation. Thank you so much for your attention. If you have any questions, please contact with me. I immediately give answers. Thank you.